Aitiip Technology Center.
Podcast.
Welcome to the podcast Conversations with our Experts. Today, we are going to discuss about WAAM, a technology that is revolutionizing industrial manufacturing. Have you ever imagined a 3D printer that uses molten metal instead of plastic? That's WAAM. In this episode, we will delve into WAAM from its beginnings to its most innovative applications. We will discover how this technology is transforming the way airplanes, cars, and buildings. We will learn about its pros, such as its fastness, economy, and versatility, and also about its challenges, such as process control and material properties. To do this, today we are joined by Alberto Laguía, Advanced Manufacturing Processes Engineer. To get deeper into the topic, welcome, Alberto.
Good morning, Isabel.
Tell us, what is 3D printing and specifically WAAM? And also, what needs arise in industries for the use of this technology?
Well, 3D printing, unlike conventional manufacturing technologies, which are basically subtractive manufacturing and Fourier processes, additive manufacturing or 3D printing is a manufacturing process that consists in add selectively, layer upon layer, of material to obtain three-dimensional objects for digital data. In this context, several years ago, Technical Committee 261 appears and they established standards for this type of technology, and also they established that all types of additive manufacturing technologies that currently exist can be integrated into 7 categories. These categories are bath photopolymerization, powder bed fusion, binder jetting, material jetting, sheet lamination, material extrusion, and direct energy deposition. Within all of these categories, WAAM is included within direct energy deposition technology. Focusing on WAAM is wire arc additive manufacturing, and this is a metal additive manufacturing technology that uses an electric arc to melt a metal wire and deposit it layer by layer on the substrate to obtain the desired 3D geometry. These type of systems are basically composed of a MIG-MAG welder machine, which is responsible for supplying the wire and producing the electric arc, and a system that allows the 3D movement to deposit the material in the desired location. Specifically, in our cell, we have the Yaskawa furnace set, Yaskawa as a robot and furnace as welder machine, to which we have added several sensors that allow us to control the construction parameters in real time, always working in a closed loop and allowing us to have more precise control of the system.
Okay, that sounds very interesting. Let's talk about applications and needs and how WAAM responds to those needs.
Well, in Aitiip for many years to know, we have been focused, particularly in our department, in the Department of Advanced Manufacturing Processes. We are focused on the production of large components. In that sense, when we began to develop the WAAM cell, we realized that there was a need in the industry to produce large-scale metal parts using this technology in order to provide it the advantages of the 3D printing, such as freedom of design, the possibility of create lightweight structures, the reduction of scrap generation, the reduction of the manufacturing time, and we also wanted to produce molds, tools, or parts with cooling circuits that will make heat transfer much more efficient.
Okay, so tell us about the applications in large-scale tooling that are being worked on now. What is being achieved and what are the needs?
Some of the applications that we are currently exploring are the production of large-scale molds and tooling, which have needs that we can provide thanks to this technology. These needs they require have to do with the ability to heat and control. Thanks to these technologies, we can manufacture free-form internal cooling ducts, which means that we are capable of making ducts very close to the areas that require the heating, making this heating and the cooling itself much more optimal. For example, last year we were commissioned to make an RTM mold for the production of carbon fiber parts for an aeronautical company. And talking a little about numbers, this finished tooling has an approximate weight of 800 kilograms, an approximate dimension of 2 by 1 by 0.7 meters. In this case, what we did was a study to determine which manufacturing process would be the most suitable. Always comparing subtractive manufacturing with the decision between WAAM and subtractive manufacturing. Well, once finished, the results extract were that using conventional technologies, a block of steel of 5 tons would have been required, which after the machining would have removed around 4 tons kilograms in waste. Through process, we print the tooling, and when we did the finishing stage to provide dimensional tolerance, the surface that require it. In this process, a total of 1,080 kilograms of steel was used, and after the machining stage, only 240 kilograms of waste were generated. This means that thanks to the use of this technology in this tooling, we were able to reduce almost 80% of scrap. We were also able to reduce the manufacturing time, reducing it by almost 23% compared to the conventional manufacturing methods. In the same context, we have printed some plastic injection molds, both in steel and aluminum, which are now in full production. And to speak of other industrial sectors, we have also primed with this technology some prototype parts for the construction or naval sector.
Okay, and what services can we offer in this line from Aitiip Technology Center?
Well, at Aitiip, I'm focusing only in this type of 3D printing technology. We can offer our part manufacturing service, making several iterations with the customer to try to adapt the part design and also to ensure that it can be printed. On the other hand, we offer the transfer of knowledge to the customer, to other companies, as well as the installation of this type of cell in the customer facilities from the commissioning to the first prints.
Okay, thanks Alberto. And finally, tell us about the future of what can be implemented in our machine.
Turning to the future, at Aitiip, we have planned an upscaling of the device, trying to mount it on a mobile system that allows us to move it through the whole working area, giving us more flexibility to carry out several jobs at the same time, and also giving us the possibility of manufacturing larger parts. On the other hand, we are also thinking or we are interested in developing and integrating new materials into our cells, such as from the point of view of molds, copper, to be able to optimize all internal thermal transfer of these molds, and also inbar to try to reduce the problem that arises in the dimensional tolerance. And more or less that is the future for our machine in a short period of time.
Okay, thank you Alberto. Thank you very much for your attention and detailed explanation. And to you listeners, we will see you in the next installment. Thank you for listening.